Deep eutectic solvents, DES. What are deep eutectic solvents? Deep eutectic solvents are a class of green solvents formed by mixing two or more components, typically a hydrogen bond donor HBD and a hydrogen bond acceptor HBA. These components interact through hydrogen bonding to form a stable liquid mixture with a melting point significantly lower than that of the individual components. Hydrogen bond donor HBD such as choline chloride, lidocaine, alanine, glycine, proline, histidine, nicotinic acid, choline fluoride, betaine, etc. Hydrogen bond acceptor HBA such as urea, glycerol, adipic acid, acetamide, phenol, benzamide, benzoic acid, succinic acid, oxalic acid, lactic acid, citric acid, glucose, decanoic acid, fructose, dodecanoic acid, menthol, thymol, naphthol, etc. A classic example is choline chloride, HBA, and urea, HBD, liquid at 12 degrees Celsius. Even though each component alone is a solid at room temperature, DES are inexpensive, biodegradable, tunable, and often derived from natural or readily available materials, making them attractive alternatives to traditional organic solvents or ionic liquids. Why are DES important? Green chemistry. DES are usually non-toxic, non-volatile, and biodegradable, addressing environmental concerns associated with traditional volatile organic compounds. Box, cost and simplicity. DES are simple to prepare usually just by mixing and heating, with no need for purification. Many components, example, sugars, acids, amino acids are cheap and bio-based. Tunable properties. By changing the components and their ratios, you can design DES with specific polarities, viscosities, acidities, or metal binding abilities, making them application-specific. How do DES work in metal extraction? DES have shown great promise in extracting valuable metals, as Li, company, Ni, Mn from complex matrices like waste batteries, example, Li-ion. Catalysts, electronic scrap, mechanism. The acidic or chelating nature of the DE helps break down the metal oxide structure. Certain DES, example, choline chloride citric acid, create an environment where metals are solubilized and remain chemically stable in solution. DES can form metal ligand complexes, aiding in selective separation. They also function at mild temperatures from 60 to 80 degrees Celsius, avoiding the energy demands of pyrometallurgy. Examples of DES in research and industry. Decomposition use case, choline chloride and urea solution, zinc extraction from metallurgical slag, choline chloride and citric acid solution, lithium, cobalt, nickel, extraction from spent lithium-ion batteries, choline chloride and oxalic acid solution, gold, A-U, silver, A-G, copper, C-U, separation from E, waste. Comparison to ionic liquids ILs. Feature, ionic liquids, deep eutectic solvents. Cost, high, low. Toxicity, variable, some toxic, generally low. Preparation, complex, often synthesis required. Simple, mix and heat. Biodegradability, limited, often biodegradable. Viscosity, often high, tunable. Future applications of DE. Battery recycling, lithium-ion. Ni, M-H. Pharmaceutical synthesis. Biomass fractionation, example, lignin separation. Protein and enzyme stabilization. Carbon capture and storage. Because of their versatility, environmental compatibility, and low cost, DES are increasingly seen as a next-generation platform for green chemistry in both lab-scale and industrial applications. Conclusion. Deep eutectic solvents offer a sustainable alternative to conventional solvents and open new avenues for metal recovery, resource recycling, and green manufacturing. Their adaptability makes them a powerful tool in designing safer and more efficient chemical processes, especially in circular economy strategies.